Value stream performance indicators are related to product and process quality, process flow, and key factors affecting all these metrics. These are some process flow metrics. Throughput, number of items processed per unit of time. Cycle time, time elapsed between two consecutive outputs. Takt time, cycle time required by the customer or market demand. WIP, work in process, number of items being processed or waiting to be processed. Lead time, total time in the system, process plus waiting. Capacity, maximum throughput physically possible. These metrics can be applied to a single process step or to the whole value stream. This model represents each of the steps in a value stream. The throughput is limited by the step capacity and available WIP. The lead time is the total time from input to output including waiting time and process time. WIP includes items being processed or waiting to be processed. In a car manufacturing line, it takes 25 hours for a car from start to finish. If a car leaves the line every 2 minutes, that is the line cycle time. The cycle time demanded by the customer, or the market, is what is called takt time. This takt of 2 minutes is equivalent to 30 cars per hour. The equivalent of the formula speed equals distance divided by time, in the case of process flow, is throughput equals WIP divided by lead time. When we join a queue, we want to know how long it will take us before we leave. From Little's law, we can extract lead time equals WIP divided by throughput. In this case, if there are 26 people in the queue and they are serving 2 customers per minute, we can estimate that it will take us 13 minutes to be served. In this previous example, we want to know how many cars are in the process. For this, we derive from Little's law WIP equals throughput times lead time. So, we can estimate that there are 750 cars in the line. In this example, a line has 4 workstations, each performing a process step. Each step takes 10 minutes, so the lead time for each unit will be 40 minutes. We have 1 unit being worked on in each workstation, so total WIP in the line will be 4 units. Takt time of the line is 10 minutes, which is equivalent to a throughput of 6 units per hour. In this other example, the curve on the left represents the cumulative number of items started in the line. The curve on the right is the cumulative number of units finished. From hours 0 to 25, the process is stable. The starts line is parallel to the finishes line. The horizontal distance between these two lines represents the lead time, time elapsed between one item being started and being finished. The vertical distance between the two lines represents the WIP, number of items in the system in that moment in time. We assume that each item being started must wait its turn in a queue until all the items which are already in the system are processed at the throughput rate. The total time in the system for this item will therefore be the time to process all the items in the system including itself. From hour 25 to 30 we have decided to stop all starts in the line. As a result, the WIP has been depleted. From 20 units it has gone down to 10, and therefore we see that lead time has also been halved, from 10 hours to 5 hours. From hour 30 onward the line is also stable. The throughput of the line in this chart is the slope of the finish line. Its value is 2 items per hour. We can see that the slope has remained constant all the time, therefore lead time varies proportionally to WIP. Lead time equals WIP divided by 2. All metrics have variation, so we must deal with this fact. Variation can be measured with a run chart to see the evolution over time. A frequency distribution chart shows the frequency of the different values. Effects of variation in the value stream. The first effect is decommitment with the customer and drop of on-time delivery, OTD. then an accumulation of WIP which may cause an increase in the lead time seen by the customer. Also, there may be a drop in throughput. When we analyze the value stream variation, we first need to know if it is stable, only random variation, or there are special causes of variation. Statistical process control will help us know this. These special causes of variation will have to be dealt with first, in our analysis. In this example of our body weight statistical process control, we notice a significant increase in weight starting on the 9th of June. If the value stream is stable, the frequency distribution histogram is a good characterization of its behavior. The customer requirements for this metric is represented by 1 or 2 spec limits. So, we want to know to what extent is my value stream able to meet these limits. A metric to measure this is CPK, calculated from the mean and the standard deviation. Defect rates follow a Poisson distribution, and we can use 2 capability metrics, DPU and DPMO. In this example of 1 defect in 3 boards, DPU is 0.33 defects per board. From the board assembly process point of view, there is 1 defective component out 36 components used, which is 27,777 defective components per million opportunities. DPU, defects per unit, is a metric from the customer perspective. DPMO, defects per million opportunities, is a useful internal metric for process improvement. A value stream map allows us to understand who does what and when. We should build the map after a visit to Gemba, where things are happening, to make sure it represents the current reality. One alternative is to make the VSM directly in a spreadsheet in the cloud where all team participants have write access. Both process description and data can be easily typed, or entered with voice, with any smartphone. A static value stream map is a good start to understand how the value stream behaves. A snapshot of the WIP situation along the line may not be representative of the normal operation. VSM simulation provides a deeper understanding of the process behavior, and it enables what-if studies to optimize the process. Tests and controls are key steps in a value stream. In case of reparable products, you may have an associated repair station to repair faulty products and test them again. A key metric in this case is the test first pass yield, the percentage of products that pass test OK the first time. When product quality drops, this will show in a drop of first pass yield and an accumulation of WIP before test and before repair. This will cause a delay for the whole value stream. Apart from measuring product quality on delivery, it is important to estimate the time it will take until it fails. Mean time between failures, MTBF, is the total operational time divided by the total number of failures. MTTR is the mean time to repair. See in Polyhedrika blogspot.